Okay, so next we will come to that unsymmetrical spans, that is supports at different levels, right. So that means suppose you have one support is here A, another is here at B. So they are not at the same level, they are this A and B two different levels, right. And this is the point that you are what you call that of that lowest point O, and from here this distance is from O to A, it is x1, and this side O to, actually if you make this is A, if I make this is your A dash, then O A dash is x1, and if this is B, if we make this is B dash, then your O B dash is x2, right. And distance between these 2 points, that is A dash and B dash, it is horizontal distance, it is L, say, right. And from this point B dash and B dash, this distance is d2, and A dash distance is a1, and your from here to here distance is h is equal to actually d2 minus your d1, right. So this is actually figure 5 supports at different levels. Now from equation 54 we know that y is equal to w x square upon 2t, this we know. Now when y is equal to d1, I mean this one, x is equal to x1, I mean this is that your what you call coordinate of the point, right. x1 d1 is the coordinate. So that means you can write d1 is equal to w x1 square upon 2t, this is equation 58. Similarly when y is equal to d2, right, I mean this one x is equal to x2, therefore this equation you substitute. If you do so, you will get d2 is equal to w x2 square upon 2t. So this is equation 59, say, right. Now from this figure h is equal to, from this figure your h is equal to d2 minus d1, this is your h. So here you can write that h is equal to d2 minus d1, right. So this is your d2, this is your d1, you substitute here, So what you will get, that h is equal to d2 minus d1. So this is, say, we are writing equation 60. Now d2 and d1 from the previous two equations you substitute, right, 59 and 58. So it will become h is equal to w upon 2t, it will become x2 square minus x1 square, this is equation 61. Also from figure 5, that means this one, also figure 5, this is the horizontal distance L, L is equal to x1 plus x2, right. So from this figure, therefore your L is equal to x1 plus x2, this is, say, equation 62. Now from equation 61, this equation we can write x2, this is a square minus b square formula. So x2 plus x1 into x2 minus x1, that means we can write from this equation that x2 minus x1 is equal to 2th divided by w x1 plus x, just cross multiply, and this one you write x2 plus x1 into x2 minus x1. Therefore x2 minus x1 is equal to 2th divided by w into x1 plus x2, this is equation 63, and this is x1 plus x2 is equal to L, and x2 minus x1 is equal to 2th upon w x1 plus x2. So these two equations you can solve. So solving equation 62 and 63, this one you write x2 plus x1 is equal to L, and this is x2 minus x1 is equal to this one. So solve this equation, these two equation if you solve, then you will get x2 minus x1 is equal to 2th upon wl, this is equation 64. Now so solving equation 62 and 64, you get that x1 you will get L by 2 minus ht upon wl, this is 65 equation number, and x2 you will get that is equal to L by 2 plus ht upon wl, this is equation 66. Now in this equation, that equation 66, if L by 2 greater than ht upon wl, then x1 is greater than 0, positive. I mean if this one greater than 0, that is L by 2 greater than ht upon wl, then x1 is positive, right. And if L by 2 is equal to h2 upon wl, then these two are equal, L by 2 is equal to this one ht upon wl, then x1 is equal to 0. But if L by 2 less than ht upon wl, right, I mean if L by 2 less than ht upon wl, then x1 is negative. Negative means that as long as it is 0 or positive, it is okay. When negative means if you extend this point A some dash line to the, it is imaginary thing, but somewhere that point O will come. So, this is because x1 is negative, right. That is why this dash line is extended from A to B this side, but in the original diagram, it was shown in different way, because this is the lowest point. So, this is x1, this is x2, but if it happens like this, then configuration may be like this, and x1 is negative means it point will be some imaginary point, right. That is the lowest point of the imaginary curve. So, that means if x1 0 is negative, the lowest point 2 of the imaginary curve dash line outside the actual span as shown in figure 6. Actually, it is outside the your what you call actual span, right. So, this is that your what you call, this is the only thing you have to keep in mind. Later when we will take the numericals, at that time we will see how things are. Now, ruling span or equivalent span, that is spans of unequal length. Suppose when a transmission line consists of spans of unequal length, say, reality it generally does not happen, but suppose the theoretical, if it happens, then theoretical tension of each span depends on its own length, that we know, because we have seen all these derivation. In fact, this is not possible with suspension insulators, since the insulator string should swing so as to equalize the tension in each span. That means, moral actually it is make generally distance between the two towers, generally it is equal distance, right. But anyway, we are saying say unequal span if it happens. However, it is possible to assume a uniform tension between dead end supports by ruling span or equivalent span. So, in that case, equivalent span, that is LE, can, if you have a different span, then LE can be taken as a square root of L1 cube, this is empirical one, L1 cube plus L2 cube plus L3 cube up to Ln cube summation divided by L1 plus L2 up to Ln. So, equivalent span and ruling span is defined as this is LE, right, or this one you can write it in sigma form, that LE is equal to root over I is equal to 1 to n Li cube divided by root over I is equal to 1 to n Li. This is equation 67. Now, where LE is equal to ruling span or equivalent span and Li is equal to each individual span in line. An approximate equivalent span or ruling span can be calculated as another formula is there, right, but this is to some extent empirical type, that is your LE is taken as L average plus 2/3 L max minus L average, this is equation 68, where L average is equal to average span in line, where L average is equal to 1 upon n sigma I is equal to 1 to n Li. Suppose you have whatever supports you have, whatever distance you have between the supports, suppose you have n number, then 1 upon n I is equal to 1 to n Li 69. So, this is L average. Now, and L max is equal to maximum span in line, right. Suppose you have so many towers are there, suppose distance are different, out of which one is the maximum, that is actually L max is equal to, that is why I have written here L max is equal to max of L1, L2, L3 up to Ln. This is equation 69 and this is equation 70. Therefore, the tension of line T can be calculated using this equivalent span length, and expression for sag is defined as we know that D is equal to, we have seen that WL square upon 80, but instead of L here we should take LE. So, LE can be calculated this way or another formula I showed you just before, right. So, D is equal to WL square upon 80, this is equation 71, right. So, in that case, so this is what you call for unequal span. Now, next one will be the effect of ice, particularly in that mountain areas that there will be heavy snowfall. So, naturally you will find that ice formation will be there around the conductor, but those thickness may not be uniform. But for our study in this course, we will assume that it is ice coating will be uniform, the thickness will remain same around the conductor. So, effect of ice, therefore, sag is determined, but as soon as that ice will be there, naturally the weight of conductor will increase, because ice also is quite the weight of ice also will be high. So, you have to consider everything. Therefore, sag is determined for the span design at which the transmission line is constructed, so that accumulation of snow or ice and excessive temperature changes will not stress the conductor beyond the elastic limit, may cause permanent stretch or fatigue failures from continued vibration. So, in mountainous areas, the thickness of the ice formed on the conductor is very significant, you have to consider, and this is true for your overhead conductor. Now, accumulation of ice on the line conductor has the following effects on the line design. Basically, one is increase the dead weight per meter of the line, because of ice that conductor weight will increase. Second thing is increase the projected surface of the line subject to wind pressure, naturally, because when ice coating will be there, so naturally that projected area will increase, and hence your what you call that it will wind pressure also will increase. So, this is actually the effect of the ice. Things are very simple. So, this one, so this is actually more likely configuration, because it is this is the ice coating and this is not uniform around the conductor, but for the your for the analysis in this course we will assume they are uniform. So, this is your conductor, this dash line is a conductor, and this is the uniform thickness of the ice, right. This is the assumed configuration, but more likely configuration is this one, but we will consider this one only, right. So, as figure 8. So, we assume that this T1 actually thickness of the ice, it is uniform, this is T1, this is T1, and this is the diameter of the conductor, and this is in the centimeter, this is also T1 thickness is centimeter, this is also in your centimeter, right, and this is the conductor. Now, the cross sectional area of the ice, you know this pi by 4 your what you call d square, that is that cross sectional area. So, when you are taking only ice we want to make it. So, find out that your what you call the total area including ice cross sectional area and subtract the conductor area. So, you will get the area of the your ice. Therefore, that cross sectional area of the ice is A I is equal to pi by 4, then diameter is d c, this is T1. So, d c plus 2 T1. So, this is d c plus 2 T1 whole square minus d c square centimeter square, because it is pi by 4 d c square is the area of the conductor. So, pi by 4 is taken common outside. So, this is the cross sectional area of the ice. Then if you simplify, A I will be pi into T1 into d c plus T1 centimeter square. So, convert it to meter square. So, A I will be pi T1 d c plus T1 into 10 to the power minus 4 meter square. Now, volume of the ice per meter, whenever we will make volume of the ice, you will see meter cube is the volume, but when we say per meter means 1 meter length. So, volume of the ice means, suppose if you assume 1 meter length, then V1 into cross sectional area. So, 1 into A I meter cube per meter. When I writing meter cube per meter means it is volume of 1 meter length of the conductor covered with a uniform thickness of ice say T1, and that means its volume will be 1 into, that means it is A I meter cube per meter. Per meter means that it is your, don't make it your m cube by m square, do not do that, it is volume meter cube, and per meter indicates that your per meter length of the conductor, right, with ice coating. Now, therefore, V ice A I we have seen pi T1 into d c plus T1 into 10 to the power minus 4. So, V ice will be pi T1 d c plus T1 into 10 to the minus 4 meter cube per meter of the conductor. This is I have marked equation say 72 and this is 72a, right. Now, let the weight of the ice be say W c kg per meter cube, right, I mean kg per meter cube, that is this is the weight of the ice. So, that weight of the ice per meter, because we have considered that 1 meter length conductor and corresponding ice coating. Therefore, W I will be this V ice whatever it is multiplied by W c, it is meter cube. So, it will be this much of kg per meter of the ice, that means W c into pi T1 d c plus T1 10 to the power minus 4 kg per meter, because this is actually kg per meter cube. So, this is your 1 meter weight of the your 1 meter length of the conductor, whose weight will be, that is this volume, your what you call that ice will be this Wc pi T1 dc plus this T1 into 10 to the power minus 4 kg per meter length, right. So, this is the weight of the ice. Then but total ice, the total weight will be, this is the weight of the ice and weight of the conductor is also there, then you have to consider both. That means the total vertical load on the conductor, because conductor weight is there W, that we have seen for the previous example, and Wi is the weight of the ice. So, it will be Wt is equal to W plus Wi. This is equation 74, where Wt is equal to total vertical load on conductor per meter length, W is equal to weight of conductor per meter length, and Wi is equal to weight of ice per meter length. So, these things are very simple. Only what you have to do is, you have to take uniform coating of the ice and find out the first cross sectional area of that this thing, how much this ice, then accordingly find out the volume of the ice for 1 meter length of the conductor. Then you consider the weight of the ice, say Wc kg per meter cube. After that you consider it, that what is the weight of the ice. This is the total vertical weight W plus Wi, right. Next one is the effect of the wind, because wind also, you know, wind pressure is also significant. Therefore, we assume that wind blows uniformly or horizontally across the projected area of the conductor. This is an assumption. We assume that winds are blowing uniformly and horizontally across the projected area of the conductor, covered without ice and with ice, right. Two things we have to do. So, figure 9 actually shows the force of wind on conductor covered without ice, and figure 10 it shows that your wind and conductor covered with ice, right. So, this is actually we have taken this horizontal, it is blowing, this is the wind, this is the conductor without anything, I mean without ice, and this is the length we have considered, say 1 meter, and this is dc is that your diameter of the conductor, right, centimeter, and this length we have considered 1. This is wind force on conductor without ice, this is the wind force. Now, we have assumed that conductor is coated with your what you call ice and uniform thickness. So, these are the wind pressure. So, in that case length is you have considered 1 meter, this is T1, thickness is T1, this is the diameter of the conductor dc, same here, same it is here dc, and with ice it is, as we have seen before, dc plus 2 T1, right, and this is wind force on conductor covered with ice, right. This way it has been drawn, right. I think it will be understandable to you. Simple thing. Now, the projected area per meter length of the, because we have considered here 1 meter length, here also 1 meter length, here also 1 meter length, we have considered 1 meter length, right. Therefore, the projected area per meter length of the conductor with no ice, right, I mean this one for this case, this is the no ice case, no ice, right. It will be SNI is equal to ANI into L, right, where SNI is equal to projected area of conductor covered without ice in square meter per meter length, right. So, this area actually projected area of the conductor covered without ice in square meter per meter length, because we have considered 1 meter length, right, 1 meter length, and this one ANI is equal to cross sectional area of conductor covered without ice in square meter, and your L is equal to length of the conductor in meter. So, there should not be any confusion here, right, multiplied this ANI into L, because this ANI actually cross sectional area of conductor covered without ice in square meter, and SNI is projected area of conductor covered without ice in square meter per meter length, right. The L is length of the conductor. Therefore, look, for 1 meter length of conductor with no ice, dc is in centimeter, divided 100. So, it will be meter into 1, it is meter square per meter. That is why that this one is the projected area of the conductor, right. This is dc centimeter divided by 100, it will be meter, and this is the length 1 meter. Therefore, it is dc by 100 into 1, the area will be meter square and slash per meter. That means, it is projected 1 meter length conductor with no ice for 1 meter, SNI will be the dc upon 100 into 1 meter square per meter. That means, per meter this is the area. this way, this is the meaning. So, I think there will be absolutely there will be no confusion, right. So, this is equation 76. Similarly, with ice, when ice covered, right, when ice covered, then again same thing you write, earlier we saw SNI, that is no ice, now SWI, that is with ice, that AWI into L, meaning is same. It is SWI is projected area of conductor covered with ice in square meter per meter length, right. AWI is equal to cross sectional area of conductor covered with ice in square meter, right, and L is equal to second length of conductor, say 1 meter. Therefore, with ice covered, the diameter is now becoming dc plus 2t1, right, dc plus 2t1. That means, SWI will be dc plus 2t1 divided by 100 into 1 meter square upon meter per meter. This is equation 78, right. Therefore, so this we got. Therefore, the horizontal force exerted on the lines as a result of the pressure of wind without ice, that is your this figure 9, right, that is figure 9, this is this one, right, without your what you call without ice. So, it will be F is equal to SNI into P, right. So, that is your P actually wind pressure kg per meter square, we will come to that. So, F is equal to SNI into P, this is equation 79, right. And when it is covered with ice and for 1 meter length of conductor, that F is equal to then dc upon 100 into P kg per meter, right. Here it is F is equal to SNI into P, and we have also seen no SNI is equal to dc upon 100 into 1 meter square per meter. So, SNI is equal to dc upon 100. Therefore, this your this SNI into P, therefore, F is equal to SNI is equal to dc upon 100, SNI is equal to into P kg per meter, right. I think it is understandable. Therefore, your F is equal to horizontal force due to wind pressure exerted on line, it is kg per meter, and P is equal to wind pressure kg per meter square. Now, with ice covered, that is figure 10, right, the same figure, this we have seen, this one, this is figure 10, this figure, right. So, that it is F is equal to SWI into P. So, for 1 meter length of conductor, we have seen SWI is equal to dc plus 2t1 upon 100 into P kg per meter. This is equation your what you call 82, right. Therefore, so wind or ice, actually there is no problem, it is very simple thing, only see this terminology division carefully, then absolutely there is no problem. So, the effective load acting on the conductor is that your W is equal to, this is horizontal force F, this is vertical, W t is equal to W plus W I, this angle is theta. For numerical purpose, this kind of figure is required again and again, this is theta, and this is W e, that effective what you call value W e. So, this is force triangle, this is the conductor actually, right. So, W e is equal to root over F square plus this is W t square, means W plus W I whole square, this is kg per meter. So, figure 11 shows the force triangle, this is that figure 11, right. Therefore, sag can be calculated as D is equal to W e L square upon 80. So, this is your actually your W e, right, L square upon 80. So, meter, this will be in meter, this is equation 84. With this, more or less little bit later you will see little bit of vibration or conductor at the end of this chapter, but with this whatever theories are there related to this sag and tension, I think we have seen everything. Now, we will go for few examples, right. So, for next is example 1 we have seen, now come to example 2. A trace crossing over a transmission line has a span of 150 meter, right, it is 150 meter. Just I am underline something such that when you will see this, it will be easier for you, right, over the stream, right. So, horizontal wind pressure is 20 kg per meter square, right, and the thickness of ice is 1.25 centimeter. diameter of the conductor is given 2.80 centimeter and weight is your 1520 kg per kilometer and ultimate strength is 12,900 kg, right. So, what you have to find out is these are the things given. Now, some data are given. So, this is the problem. What you have to find out, that use a factor of safety of 2 and 912 kg per meter cube for the weight of ice. Using the parabolic method, determine the following, that you have to use the parabolic method, that we have seen already. Weight of ice in kg per meter you have to find out, total vertical load on conductor in kg per meter, horizontal wind force exerted on line in kg per meter, effective load acting on conductor in kg per meter, then sag in meter and vertical sag in meter. These are the things you have to find out. Now, first one is weight of ice in kg per meter. So, using equation 73 we have seen Wi is equal to Wc into pi into T1 into dc plus d1 into 10 to the power minus 4 kg per meter, right. So, all the data are given, So, what you can do it, just you have to compute this, right. So, the Wc is given 912 per kg per meter cube, this is given, T1 is given 1.25 centimeter, dc is given 2.80 centimeter, Wi is given 900, then Wi you calculate, formula is given 900, Wc is 912 into pi into your T1 1.25 into your dc plus T1 2.80 plus 1.25 bracket close into 10 to the power minus 4 kg per meter. So, Wi will be 1.45 kg per meter, this is the weight of the ice. Now, next in B it is asked that you find out the total vertical load on conductor in kg per meter. Vertical load is nothing, using equation 74, Wt is equal to W plus Wi. So, W is 1520 kg per kilometer, it is actually given 1520 kg per kilometer. So, that is you divide by 1000, so it will be 1.45 kg per meter, right. Therefore, Wt is equal to 1520 by 1000 plus 1.45. So, it is coming actually 2.97 kg per meter, 1.45 kg per meter ice, although I should have written here 1 point your this thing, your this kg per sorry, this is kg per kilometer, this is weight of the your what you call weight of the ice 1.5 and this is kg per kilometer, that means it will become 1520 divided by 1000 kg per meter, right. So, and this is Wi actually, sorry, this is Wi, right. So, Wt is equal to coming 2.97 kg per meter. So, then C is horizontal wind force exerted on line in kg per meter. So, from equation 82, F is equal to dc plus 2T1 upon 100 into P kg per meter, right. So, dc is known, P is given, T1 is known. So, you can easily compute this one, that dc is 2.80, T1 is 1.25, P is 20 kg per meter square. Therefore, F is equal to this is dc plus T1 by 100 into 20 kg per meter. So, F is equal to 0.81 kg per meter. Thank you, we will be back.